Hi, everybody, and welcome to August 29th. Last night, there were some great questions about units and the relationship of pounds mass and pounds force. And what I wanted to do was put together some example problems. I think maybe to clarify, I'm not sure I did a great job explaining units cancellation and working both in SI and English units. So I wanted to put together another PowerPoint with 6 examples illustrating 6 simple examples of using units in thermodynamics. Now is the time for you to get practice working with units, because we're going to sort of take for granted that you're really, really good at working with units in these various problems, because it does get harder much more quickly. So keep up with your homework. And also, that's going to give you much more practice in dealing with units, both in SI and English. So I'm going to share my screen. And I'm going to go to PowerPoint, I hope, and slideshow. And so I'm going to show you how to access just this PowerPoint, static PowerPoint, if you want to go back and review any of the slides rather than having to look at the video and pause it. So here we go. And the chances are good that you may be thinking to yourself, how do I keep all of these units straight in thermodynamics class? So what I'm going to cover first is a trick that I learned from my own engineering professors that has helped me to keep units pretty straight, both as a student and then as a practicing engineer. So the trick has really paid off for me. And then I'm going to illustrate that trick with 6 simple examples. So I'm going to drag you through 6 examples, but I think it'll go pretty fast. And here's the trick I learned. The trick is that you can multiply any mathematics expression by unity and preserve that expression. So I thought, when did I learn this, the fundamental of this? And it was back, for me, it was back in 7th grade, where we were talking about various algebraic rules of the road. And so as an example, if you've got the expression x plus 5 and you multiply it by 1, that's unity, 1, it equals x plus 5. And you think, well, that's obvious. And I almost thought about that in 7th grade itself. That's obvious. Multiplying anything by 1 gives you anything. But it's the starting point for this little trick associated with units. Okay, and so here's a little better example. Multiplying anything by unity and getting that result. So how many inches in 1.75 feet? That is an easy problem, I hope, in feet to inches. And so here's a way to put it out on paper. You could just about do it in your head, but let's write it out on paper to be sure we're on the same page. 1.75 feet times unity. And so I hope that all of us know that there's 12 inches in a foot. And so do you see that this is unity? There's a number, 12 divided by 1, and units, inches per foot, 12 inches in 1 foot. And so now it makes it easier to do the math. 1.75 times 12 is 21. And also I can cancel my units out visually to see that I've got 21 inches on the right-hand side of the equation. Not bad, you think, what a waste of a slide, but I hope that you got it. Okay, let's go to another example. Similar example. How many meters in 1.75 feet? So now we're going to go English to SI, and we're going to apply the same trick. We're going to multiply 1.75 feet by unity. And so now this is a conversion that I have not committed to memory. I have to look it up every time. I don't have this in my head, but there are 0.3048 meters in a foot. 0.3048 meters per foot. So it's about 1/3 of a meter for each foot. Okay, so there's unity. So again, I'm going to do the math to get 1.75 times 0.3048 is 0.533 meters. And then I can cancel my units to be very satisfied that I've got the right units. Make sense? These are really easy, right? It's going to get a little harder. Now, so I've talked about online, but I bet you I've only talked to 10 students or less, and there's 75 students in the tutor group. So I want to make this point very important. You have got to be able to find this one page of conversion factors in your textbook, whether you've got the PDF version or if you have the online HTML version of the book, the ebook, or if you have a paper book. It doesn't matter. You must find this one page. And so, for example, that's where I looked for my length conversion, and I've blown it up. 1 foot equals 0.3048 meters. You must be able to find that. So find it in your book. Now, I'm going to show you, I have posted my one-page PDF file of that one page on my Jay's Toolbox Canvas site. So let me go live. I'm going to hit escape. I think I'm going to hit escape. Yes. I'm going to minimize, and I'm going to go to Jay's Toolbox Canvas site. Here we are. And I'm going to show you how to access, and you just download this file and hold it for yourself. Files. Okay. We're going to go to the tutor group. And now instead of homework problems, we're going to click on resources. And I'm going to scroll down to, it should be Moran and Shapiro conversion factor. So you click on this PDF file, you click the download icon and save it to your own computer. Please do that. Either find it in your own textbook, know how to use this one page, or somehow get a hold of that one page. All right. Back to PowerPoint. Okay. And from current slides. So we just covered that. Now, let me tell you about the 6 example problems I want to cover with you. It should go pretty fast. Given the mass of an object, what is its weight? We're going to have an example in SI, the easiest, and an example in English, a little harder. Next set of examples. What is the pressure inside a piston and cylinder when you know the piston's weight and the surroundings pressure? Sounds familiar, I hope. You said, man, that sounds like a homework problem. I'm going to give 2 examples, one in SI, one in English. Finally, what's the kinetic energy of an object of a known mass and velocity? If you know the mass of an object and the velocity of the object, let's say it's a closed system and it's moving through space, you can calculate its kinetic energy. You're going to do that in SI and English. So here we go. Example 1, a person has a mass of 68 kilograms. What is the person's weight when the person's standing on the earth? We're not going to cover anything about a person standing on the moon. Let's not go there. Okay. What is the person's weight on earth? Okay, so think about, here's a quick quiz before we go to the next slide. What units in SI is going to be a person's weight? What units will be a person's weight? Newtons. Okay, so here we go. W equals mg right out of the book. G should have committed to memory. G on the earth is 9.8 meters per second squared. I call that common sense. We were not given that number when we were students. We just had to know that. Okay, so here we go. W equals mg, 68 kilograms, 9.8 meters per second squared, 666.4 kilogram meters per second squared. And so now we've got to remind ourselves, oh, that's right. This combination of units is a Newton. That's what a Newton is defined as. 1 Newton is 1 kilogram meter per second squared, M times A. So the answer, boom, the weight of the person is 666.4 Newtons. Easy. Okay. 1 out of 5, done. Example 2, a person has a mass of 160 pounds mass. In your book, it's going to be 160 lb. And I learned to write down lbm instead of lb. And so either way is going to be acceptable for you as an engineer. lb, that's a mass, or lbm, that's a mass. What is a person's weight on Earth? Okay, think to yourself, what will the units of a person's weight be in English units? What will a person's weight be in English units? Pounds force, LBF. Okay, so here we go. Same old thing. I copied and pasted the slides and just changed numbers and units. W equals mg. G is 32.2 feet per second squared on Earth. Again, you should commit this to memory. Okay. And now I'll do the math and the units. 160 pounds mass times 32.2 feet per second squared is 5152 pounds mass feet per second squared. Now we got trouble because this set of units does not equal 1 pound force. Be very aware of that. This is a critical thing that you must know when you're taking thermodynamics. So I'm not going to squeeze it in on this slide. I'm going to go to the next slide. We need the units conversion that transforms pounds mass feet per second squared into pounds force. So let's do that. Now, I've taken a little screenshot and blown it up from your one-page conversion factors. Okay. And so I've seen this with my eyes. 1 pound force equals 32.174 pounds mass feet per second squared. And I put it into the form of unity. I did a poor job last night of explaining that, and that's why I wanted to put together this slide for you. So there's unity. That's how you turn this conversion factor in your sheet into unity, 1, basically without units. Okay, and so now I'm going to jam this in next to my numerical and units results, 5152 pounds mass feet per second squared, and I will scratch this out with your pencil and paper. You do your units check to see that the weight is 160.1 pounds force. So in a sentence, a person with a mass of 160 pounds mass weighs 160.1 pounds force on the Earth. Okay, so notice the numerical similarity between mass and force on Earth. But I don't want to dwell on that, okay? It's key that you learn the skill of conversions with units. That's the key, okay? A person with a mass of 160 pounds mass weighs 160 pounds force on Earth. Now, just a little, we said we weren't going to go to the moon, but just to spend a few seconds on that. In your mind, answer, what would a person weigh on the moon? What would this exact person, the person with 160 pounds mass, what would that person weigh on the moon? More, less, or exactly the same? The answer, of course, would be, you know good and well that a person is going to weigh less on the moon. You've seen the videos of Neil Armstrong on the moon, bouncing up and down. A person weighs less on the moon, but with the same mass. Okay, example 3. Should look a lot like a homework problem. Several homework problems you've probably already done. So this will be a good review for you. This is a classic, simple quiz question. A gas is contained inside a vertical piston and cylinder arrangement fitted with a 5 kilogram piston, and that piston has a cross-sectional area of 25 centimeters squared. Okay, so I've determined the mass. I've determined the area for you. I didn't just give you the diameter. I've determined the cross-sectional area for you. The problem, the pressure of the surroundings is 101 kPa. Finally, determine the absolute pressure of the gas inside the cylinder. Should be pretty easy problem. I hope you see, but let's go through, be sure we can do this numerically and with units. Start with a sketch. Here's my sketch, piston and cylinder. I've shown a little dashed area to show that it's a closed system. This is the gas contained inside the piston and cylinder. Okay. Also a sketch is a free body diagram. So I've shown, I study the words of the problem. I've got the weight of the piston pushing down on the piston. I've got the pressure of the surroundings pushing down on the piston, and what's pushing up on the piston is the pressure of the system, the gas in the system, times A of the piston. So all I have to do is go right to statics class, do the free body diagram. I have to exactly balance the downward and upward forces, come up with one equation and one unknown, and then I can solve for the unknown P of the system. So I'm not showing all those steps. You're smart enough to get those steps done. So P of the system is P of the surroundings plus the weight of the piston divided by the area of the piston. So that's going to be your governing equation. You won't find it in the book. You should be able to derive it yourself. All right, so we're going to work through. And so my suggestion is, look, in these thermo problems, when you're given square centimeters, the best thing to do is transform a cross-sectional area into square meters from square centimeters. So we're just going to do this unity trick again, conversion and unity. 25 centimeters squared times unity. 1 meter times 1 meter in the numerator, 100 centimeters in the denominator, and that's going to be, so that's 10 to the minus fourth, isn't it? So it's 25 times 10 to the minus fourth square meters. And of course, you can go through and get your units cancellation. So you've got the area of the piston in terms of square meters. Now, some instructors say, don't do any of the intermediate math, save all of the math for one last monstrous equation. That's okay, you can do that. However, that's not the way I taught myself. So for me as an engineer, I tend to do a lot of intermediate numerical results. So that's just a judgment call. That's up to you all and to your instructor. So this is an intermediate little piece of work. Area of the piston, 0.0025 square meters. Next is, okay, I've got my sort of governing equation that I derived, P of the system, and now I'm going to write out numbers and units. P of the surroundings, 101 kPa. Mass of the piston, 5 kilograms. G, 9.8 meters per second squared. A of the piston, 0.0025 meters squared. Okay, great. I've got to be very careful here. So notice here, I have to remember what is a Pascal? What is a PA? A Pascal, it's a Newton per square meter. So I'm going to write down on my paper 101. I'm going to put down, instead of kPa, kilonewtons per meter squared. Notice here, so I'm going to do the math and keep my units. 5 times 9.8 over 0.0025 is 19,600 kilogram meters per second squared divided by meter squared. Oh, so I've got to see if I've got a match here or not. Let's go to the next slide. So do you see what I did? See that? Okay. And then with my eyes, these aren't matching exactly. I still got some work to do. Okay. So this was from the previous page. Okay. And notice here, kilonewtons per square meter. Let's look at this. What is a kilogram meter per second squared divided by meter squared? So I've got to, okay, so you see I've got to do that. Well, there's a Newton, there's a meter squared. And so I've still got a units mismatch. I've got 19,600 newtons per square meter. And over here, I've got 101 kilonewtons per square meter. So I've got to do one thing or another. And so what I did in the solution was I said, I'm going to change everything to kilonewtons per square meter, or kPa. So on this right-hand side, you see I'm going to slip 3 decimal places to get my K here. So do you see what I did? Okay. Newtons per square meter goes into kilonewtons per square meter by slipping this 3 decimal places. Now I got all my units straight. And so I've got my answer. The system pressure is 120.6 kPa, 120.6 kilonewtons per square meter. And I wrote that out in a sentence. Okay. I'll let that soak in. Remember, you can get this. I'll show you how to get to this static PowerPoint if you want to look at this in specifically. Okay, example 4. Same situation, different unit systems. A gas is contained in a vertical piston and cylinder fitted with 20 pounds mass piston, and that piston has a cross-sectional area of 8 square inches, 8 inches square. The pressure of the surroundings is 14.7 psia. Here's the job. Determine the absolute pressure of the gas inside the cylinder. Okay. It's going to be the same approach. In fact, I can copy and paste the sketches and setup. So I've done that. All I did was change the numbers in the units. So in creating the presentation, it was really pretty easy. Okay. And so you derive this exact same result. But now we've got to go through the mathematics and the units. P of the system is P of the surroundings plus W piston over A. Weight of the piston. Okay. Okay. And so work through, it says, let's look at some units. P of the system, okay. P of the surroundings given as 14.7 pounds force per square inch. Units over here, W piston over A, pounds force not of the piston, not given. A of the piston, 8 square inches, given. Okay, so I've got to figure out the weight of the piston first, I think, as an intermediate piece of work before we move into the final solution. Okay. So I'm hoping that I'm dragging you through this and doing enough repetition so you catch on. The weight of the piston is M times G. Mass, 20 pounds, G, 32.2 feet per second squared. I've now got to multiply this by my conversion, 1 pound force in the numerator, 32.176 pound mass feet per second squared in the denominator. That's unity. I'll do all my canceling, and the weight of the piston is 20.02 pounds force. Okay. Numerically, very similar to the mass, but not equal to the mass. Okay. Very similar. The weight of the piston is 20.02 pounds force. All right. So we're going to trudge ahead. What's our job? Our job is finding P of the system. We don't want to get lost. Okay. So now back to our governing equation with numbers and units. P of the system, 14.7 pounds force per square inch plus 20.02 pounds force divided by area, 8 square inches. And so, there we go. Look at this. Our units are consistent. That's looking good. So we just do the math, and we've got, well, I've got to do this math, and it looks like it's 17.2 pounds per square inch. And so remember that these are identical units. Pounds force per square inch is PSI absolute. PSI absolute. That's what PSI stands for. And I've written out in a sentence, the absolute pressure of the gas in the cylinder is 17.2 PSIA. That's engineering jargon. That can work. Okay. And this makes sense, doesn't it? So if we went back to the sketch, we'd see that the absolute pressure inside the piston and cylinder is a little higher than the surroundings pressure. Makes sense. All right. Hopefully there's some repetition here. I hope that it gives you an ability to sort of, okay, I'm catching on here, I think. Now let's move to kinetic energy. Example 5, the mass of a bowling ball is 6 kilograms. The bowler rolls that ball down a level alley, and the speed of the bowling ball is 27 kilometers or kilometers per hour. 27 kilometers per hour. Determine the kinetic energy of the bowling ball. Okay. What will units of energy be in SI? Units of energy in SI. I think it's going to be, should be joules. And a joule is a Newton meter. Okay, so there we go. And the sketch is easy. There's a ball, the mass, velocity given, easy sketch, kinetic energy right up out of your book, 1/2 mv squared. Pretty easy. All right. And then recognize the units of kinetic energy for SI are going to need to be either joules or kilojoules. Remember, a joule is a Newton meter. Joule is a Newton meter. All right. Here's what I do in my solution. First thing I do is get the velocity into sort of standard SI units, meters per second. So we're going to go through the same drill of unity, 27 kilometers per hour. Well, that's going to be 27,000 meters per hour. And then unity. There are 3,600 seconds in 1 hour, 60 times 60. Okay. 3,600 seconds per hour. And so we do the math, we do our units cancellation, and we get the velocity 7.5 meters per second. It's our intermediate work. Kinetic energy, 1/2 mv squared. We jam in our units, we jam in our numbers, and we get 168.8 kilogram meter squared per second squared. All right, are we in trouble or not? Can we visually see if are we in good shape or are we in trouble? Well, what let's do is let's split out this meter squared into a meter and pull it out here so we can visually see that we've got kilogram meter per second squared. That's a Newton. And we've got this little extra meter here. Sure enough, we've got 168 Newton meters. And so the energy of the bowling ball is 168.8 joules. And that's our answer. Pretty easy, isn't it? Really want to encourage you to get very comfortable with these units and encourage you to take the time to write this level of detail down on pencil and paper in your solution. It's going to pay off for you in your grades. Example 6. Okay, now we've got a bowling ball that has a mass of 13 pounds mass. The velocity of the bowling ball is 17 miles per hour, mph, miles per hour. Determine the kinetic energy. All right, well, what are the units in English for energy going to be, just for energy? I think the simplest form would be foot-pounds force. Force through a distance, foot-pounds force. Same old sketch, same governing equation, just different numbers and units. Kinetic energy in units need to be foot-pounds force. So my intermediate work, I'm going to transform my velocity into traditional velocity units in English, feet per second, not inches per second, certainly not miles per hour, feet per second. Okay, so good experience now in multiplying sort of by unity twice. 17 miles per hour. We know there's 3,600 seconds in 1 hour. Okay, that's unity. And also, I'm going to have to tell you that in 5th grade, I had to learn that there were 5,280 feet in a mile. So nowadays, you may not have been required to learn that, but as an engineer, I hope that you learn it. 5,280 feet in 1 mile. So again, notice this unity. 1 mile equals 5,280 feet. So we're going to do the math. We're going to cancel our units. The velocity is 24.93 feet per second for this example problem. All right, now we're going to go to our governing equation, 1/2 mv squared. I've got an itchy nose and I apologize. 1/2 m, 13 pounds mass. Velocity squared, 24.93 squared, feet squared per second squared. Okay. Do the math, 40.9 pounds mass feet squared per second squared. This is not a foot-pound force. We've got more work to do. We got to get our units straight. So here we go. We're going to go back to our 1 page. We're going to remind ourselves of this conversion. Remember the trick on multiplying by unity. So we write down our kinetic energy number and units, write down our expression for unity, cancel our units. Okay. Notice here, there's a little tricky. Do you see that what I did was I marked out the square, the exponent 2 on feet, because I've only got foot down here. So I've got a remaining foot up there, okay, and I've got a pound force there. And so my kinetic energy is 125.6 foot-pounds force. And so the result is, in a sentence, the kinetic energy of the bowling ball is 125.6 foot-pounds force. Now, let me show you. I'm going to escape out of PowerPoint, I think. Whoops. And I'm going to show you how to get to this PowerPoint if you want to go static. Let's go to Files. So now we're in Jay's Toolbox Canvas site. Let's go to Tutoring. Boy, I hope it's there. Click on Resources, and let's scroll down. Here it is. Working with Units demo. So you can click on this and download the presentation if you wish to look at this slide by slide. Okay, where are we? Files, tutoring, resources folder. Okay, I feel your pain. English units are hard to use. There's no getting around that. Don't let anybody convince you, oh, it's easy, it's a snap. It is not. English units are tough. So why are we mean people, mean engineers and instructors? Why are we requiring you to use English units? The real world reason is that when you get out and work in industry or even in federal government in the US and many applications, English units by far and away are used throughout industry and manufacturing, in transportation, in your real world. Those of you that have tools, those have tools in your toolbox, physical tools, those typically are an English system in terms of wrenches and things like that, spark plugs. So it's the cold, cruel world. So sorry about that. They're hard to use. You have to learn how to use them and like them. But remember the trick. You can multiply any mathematical expression by unity and preserve the expression. So it is my hope that you see how to use sort of that trick about conversion factors and unity so that you can deliver yourself to the promised land in working in the English set of units. So that's what I've got. Let's see. I'm gonna try to. There we go. I'm trying to figure out where to go. I'm going to stop sharing. Yes. Okay. I hope that's helped. I hope that helps everybody. Do not hesitate to keep asking questions. But I just wanted to share this with you because the sooner you can become a master at dealing with units, it gets harder faster, and you're going to be able to spend more time problem solving than having to spend so much time on units. Okay, so good luck. I hope to see you online, but certainly keep visiting Jay's Toolbox, both the Canvas site and the public site. All right, see you again soon.